Let's picture this. You're sitting at a red light next to another car. The light turns green. One driver just kind of eases on the gas, slowly creeping up to speed, while the other completely floors it, blasting off the line. Now, both cars are moving, sure, but that second car, it's experiencing way more acceleration. We throw this word around all the time, right? Acceleration. But what does it actually mean? Is it really just about going faster? Well, we're going to challenge that exact misconception right out of the gate.
Welcome to The Explainer. So glad you're here. Today, we are completely demystifying the physics of acceleration. We're tossing out the dry textbook jargon and looking at this for what it truly is, the fundamental science of change in motion. This is the invisible thread that connects motion, force, and time. It's the reason vehicles move, the reason rockets can punch through the atmosphere, how athletes sprint, and even how planets stay in orbit. Stick with me, because by the end of this explainer, you are literally going to see the world moving in a completely different way.
All right, here's our quick roadmap for today. We're going to see why acceleration is way more than just going faster. Dive into the math of motion, break down the types of acceleration, explore force and motion, and finally, look at some really wild, real-life applications.
Part 1. More than going faster.
Okay, let's completely bust the biggest myth about acceleration right now. Most people assume it exclusively means speeding up. But in physics, it's so much deeper than that. Acceleration is literally any change in velocity. Which means, yeah, it happens when your speed increases, but it also happens when your speed decreases. That's right, slamming on your brakes is a form of acceleration. And here's the real mind bender. Just changing your direction, like smoothly turning a corner at the exact same speed, that absolutely counts as acceleration too.
So, let's lock in our absolute foundation before we get into the numbers. Here is the formal definition. Acceleration is the rate of change of velocity with respect to time. It's not just a measure of how fast you're going, it tells us exactly how quickly your velocity is changing. It's the measurement of the change itself.
Let's move to part 2, the math of motion.
Let's walk through a super practical example. Imagine a car is starting from a dead stop. That means its initial velocity is 0 meters per second. Now say after 5 seconds, its final velocity reaches 20 meters per second. The car's velocity just jumped by 20 in a span of 5 seconds. So you just take that 20 divided by 5 and boom, you get an acceleration of 4 meters per second squared. But what does that actually look like in reality? It means that for every single second that ticks by, the car's velocity steps up by exactly 4 meters per second. At 1 second, it's doing 4. At 2 seconds, it's at 8, then 12, 16, and finally 20. It's a constant, perfectly measurable stair-step of speed.
Taking that concept and dropping it into our standard physics toolkit, the base formula is A equals V minus U all divided by T, where A is our acceleration, V is the final velocity, U is the initial velocity, and T is time. And the standard SI unit, meters per second squared. Why squared? Well, because you're dividing velocity, which is already meters per second, by time, which is seconds. And hey, for the dimensional analysis fans out there, it's m0 L1 t minus 2, which just means acceleration doesn't care about mass, it only relies on length and time.
Now for part 3, the types of acceleration.
We can easily contrast the two most common types right here. On one side, we have positive acceleration. This is what you instinctively think of, velocity increasing over time. You know, merging onto the highway and going from 20 to 80 kilometers per hour. But on the flip side, we have negative acceleration, which you might hear called deceleration or retardation. This is simply velocity decreasing over time, exactly like hitting the brakes for a red light. Same math, just pulling in the opposite direction.
I know it's super easy to get tangled up in the jargon here. People use speed, velocity, and acceleration like they're the exact same thing, but they are incredibly different. Think of speed as just distance traveled over time. It's a scalar quantity, meaning it only has a size or magnitude, no direction. It just answers the question, how fast? Velocity, though, is displacement over time. It's a vector quantity, so it has both magnitude and direction. It answers how fast and which way. And acceleration, that's the change in that velocity over time. Also a vector, dependent entirely on that velocity change and measured in our trusty meters per second squared.
So if you remember nothing else, remember this simple equation. Speed plus direction equals velocity. And because acceleration is a vector that depends on velocity, simply changing your direction creates acceleration. Even if your speedometer doesn't budge one bit, if you take a circular turn in your car, you are accelerating. Physics calls this centripetal acceleration. It's the exact same reason why the moon or a satellite up there orbiting Earth is continuously accelerating. Its direction is literally changing every single millisecond.
All right, part 4, force and motion.
Time to bring Isaac Newton into the mix. Acceleration is fundamentally tied to force through Newton's second law of motion. F equals ma. Force equals mass times acceleration. This elegant little equation tells us that applying more force gives you more acceleration. Imagine pushing an empty grocery cart. You can get that thing flying down the aisle with barely a tap. But, and here's the catch, more mass means you get way less acceleration from the exact same force. Try pushing a broken down, fully loaded moving truck. Way harder than pushing a bicycle, right? The mass literally resists the acceleration.
So how do physicists actually visualize all this? They use velocity time graphs. And on these graphs, the physical slope of the line is the acceleration. A straight line pointing up means constant, uniform acceleration. Now, a totally horizontal flat line doesn't mean you've stopped moving. It just means zero acceleration. Your velocity is perfectly steady, like setting the cruise control on a long highway drive. And a falling line? You guessed it, that's our negative acceleration, or braking.
For the hardcore math folks mapping out uniform acceleration, here are the big 3, the equations of motion. These formulas mathematically link displacement, which we call s, with initial and final velocity, acceleration, and time. These are the literal tools engineers use to predict exactly where a moving object is going to be at any precise moment in time.
Which brings us to part 5, acceleration in real life.
Take a look at this number, 9.8 meters per second squared. That right there is Earth's gravitational acceleration. It's an invisible, relentless, uniform acceleration pulling on absolutely everything near the Earth's surface. If you drop an apple, and let's just ignore air resistance for a second, its speed will increase by 9.8 meters per second every single second it falls. It's a constant force shaping our entire reality. Let's look at some things you can really feel. Think about giant rockets launching into space. They require absolutely massive, sustained acceleration just to break free from that 9.8 meters per second squared pull of gravity. Or think about riding a roller coaster. The entire thrill of the ride, that stomach-dropping sensation, comes purely from sudden extreme changes in acceleration during steep drops and incredibly sharp turns. Even something as mundane as an elevator. When it first jerks upward, you feel a little bit heavier for a second, right? That is the physical sensation of acceleration pushing into you.
This stuff isn't just theoretical. It's the backbone of modern engineering. Engineers harness the rules of acceleration to build massive things: safer cars, jumbo jets, spacecraft, advanced robotics. But it's also sitting right there in your pocket. Modern everyday tech runs on it. Your GPS, your car's navigation, and yes, your smartphone, they all have tiny little accelerometers packed inside. They are constantly measuring the movement and rotation of your device, which is exactly how your phone knows when to flip the screen to landscape mode or how to count your footsteps. So the core takeaway of this entire explainer really boils down to this quote right here. Acceleration is not just about going faster. It is the science of change in motion. Keep that rule of thumb in your back pocket. Speed tells us how fast. Velocity tells us how fast and which way, but acceleration tells us how quickly that velocity is changing. From dropping your keys to a rocket blasting into orbit, it is literally everywhere. I want to leave you with one final thought to chew on today. Where do you feel acceleration the absolute most in your daily life? Is it hitting the gas pedal on a highway on-ramp, riding the subway, or maybe getting whipped around on an amusement park ride? Pay attention to that invisible math working around you the next time you feel that push. If you found this explainer eye-opening, be sure to share it around and subscribe for even more amazing deep dives into the science of our world. Keep questioning and keep learning.